Sorry.
Hey, Marcus.
Hi, Carlo. Hey, everyone. Hey.
Nice to see you.
Yeah, nice to see all of you. Hey, should come back to Vienna soon.
Well, we are making plans for next year for the conference for sure, but maybe even earlier.
Remember, you should include February. It's ball season. At some point you should have that in your in your schedules. And if you know, we can arrange something.
You know that they're now in Madrid, Marcus, Francesca and Carlo.
So that's a very short travel. Very good.
Okay, I think we've got plenty of people piling in, and I think it's a good time to get started. So, okay, welcome everyone. Today we've got the QSS seminar hosted by Marius Christodoulou on the topic of space-time in the superposition in the laboratory. These virtual seminar talks are approximately 30 to 40 minutes long, and the talk is being live streamed and recorded. For anyone in the audience, please feel free to ask any clarifying questions, especially if the talk is technical. On the other hand, we'll have plenty of time at the end for questions which are likely to lead to kind of longer form discussion. Okay, so with that, I'll give the floor over and say to Marius, thanks for agreeing to give a seminar, and take it away from here.
Thank you. Thank you very much, Matt, for organizing the seminars. All right, so let me get straight to it. I will be talking about tabletop quantum gravity tests and some aspects of it. In particular, I'll try to discuss a bit what interests me in the direction of trying to understand better whether there could be more clarity on the search for a no-go theorem. I'm not actually working on no-go theorems myself, but I'm trying to clarify some aspects and a few possible alternatives to the standard mediated entanglement experiments, including in the end a new idea we have with Alejandro Perez and Carlo about possibly using this type of quantum sensing to detect dark matter that is at Planck mass, which could be tiny black holes. All right, so first of all, let me say that there's many previous seminars that are related to what I am about to say and have covered various aspects. So Flaminia recently talked to us about a generalized, let's say, a description of mediated entanglement with delocalized sources, which I think is something that people are getting into more and more and is very interesting. Plenia also talked about the same topic from a different perspective, from the perspective of phase space with Wigner functions. Previously, Jonathan talked to us about his approach to what he claims to be a consistent theory that combines gravity and quantum without actually quantizing gravity. Boval talked about aspects of causality and complementarity and the possibility of understanding the mediating degree of freedom to be space-like quantum fluctuations of the field. Chiara talked to us about how one might think about all this in a theory-independent way. Sugato about his idea that kickstarted all this a few years ago on how to, in practice, do an experiment involving path superpositions. Marcus talked to us about more the feasibility aspects, the coherence, the idea of creating entanglement between oscillators, and research about the idea of using bose-einstein condensates. So I will be touching on all these topics. sorry for the slow introduction, to say that it's impossible to cover these topics comprehensively. So now I'm estimating about 1,000 papers. So you can go also to the seminars to look for more information. I will be referencing them as I go ahead. So brief history. The story starts from 1957 when Feynman made the point that if we source the gravitational field by quantum mass, then this should create a quantum gravitational field, and then maybe we can use another mass to witness that. Now, I want to emphasize that what he had in mind is conceptually the same thing, the correct thing, but in practice is quite different because he had actually in mind detecting the the deflection of the test mass. So the test mass actually falling in the field, which is not really feasible to do. But the main idea is still the same. So yeah, so basically the idea is that given that we learned from Einstein that matter sources a space-time geometry, then we expect that quantum matter is going to be sourcing a quantum geometry, and very schematically writing that equation down, we should have something of that sort. And so creating a quantum matter that is mesoscopic or macroscopic, that we can detect its gravitational field, might allow us to learn something about quantum gravity. Now, this is so nice and simple, but of course, it's much more complicated than that to get anything out of it. Now, what is now called tabletop quantum gravity or low energy quantum gravity and so on was kickstarted by these papers here, although ideas go way back, and there is many more that have contributed to this. So with this, somehow interest was provoked with this simple picture that you put a quantum mass on the left, a quantum mass on the right, they get entangled, and you imagine the field that is entangled them to be the mediator, you know, from quantum information and thinking about quantum circuits, that if this happens, the mediator should be a quantum channel, right? So what's the importance of all this? Well, there is a big selling point here, which is essentially these 3 lines that I'm writing here, that what one would like to say is that if the left and the right quantum particle became entangled through gravity, then gravity cannot be a classical variable, and our established theory for gravity is a classical field theory, therefore it will be falsified, which is no small thing to falsify general relativity. It's been standing solid for 100 years and has been tested to excruciating precision. Now, what exactly would be this effect that would be witnessed? Well, there is a very big discussion about that. The one that I like most is obviously the one that I suggested with Carlo, but I will be also critical about that as we continue. So the idea is basically that, look, what's going to happen, and this is really what Feynman was saying also in 1957, if you read the report, is that, look, if you create some superposition of quantum matter, and in particular, if that is of the sort, you know, it's a quantum controlled superposition, so I have many classical branches, I put them in superposition, that gives me something quantum, then the field would also be in a superposition, which is quite cool, right? Because we're talking about seeing space-time in a quantum superposition in the laboratory. Now, I think that this is getting accepted, like as a, you know, way to talk about this colloquially. Now, of course, this is, how to say, where you're essentially assuming already some sort of quantum theory of gravity, and you're interpreting the effect within that theory as arising because that theory has this feature. So this is what we would call the theory fixed interpretation. Now, before I go on to discuss these subtleties, I just wanted to mention that in practice, it's not very clear how exactly these experiments might happen. And the ones that I'm most familiar with are obviously the things that are happening in Vienna that Marcus here is leading. And there's a lot of work going into learning how to create very delocalized states so that will be continuum variable superposition, not like a left and the right, but you have really a big delocalized wave function. You have them interact. You have two of them, they interact, they get entangled, and so on. And there's a very nice discussion here in this paper about the challenges of avoiding decoherence. Yeah, so one work that we put out recently with Marcus and Ofek and Andrea had to do with understanding these two types of protocols, the path superposition and the oscillators, so with the localized continuous variables, as in a common framework using the path integral, and make the point that you can understand the entanglement generated in this setting also as a superposition of spacetimes, continuum superposition in this case. And there's been, as I said, there's these references on the bottom. There's various people now, in particular Flaminia and Linchin, and also Plenio, so both of the previous key seminars were talking about these works that are where one can see that there's even more general setting than what I'm describing here. What I'm describing here is that you have a left and right superposition for each particle, but each particle has its own spread. And so this encompasses both the oscillator and the path protocol, which you can recover as different limits, which has these formulas that I'm giving here. But I just wanted to make the point that there is even more general protocols, and I'm not quite sure what to do there, but this is something I am thinking about also with my students and discussing with Marcus, and I do think it's interesting to see whether there is anything more to be seen, or if there is a smarter way of doing the experiment by thinking of more general quantum states for quantum matter than, you know, the Stern-Gerlach type path superposition or the oscillator states, which are pretty much the simplest thing you can think of. Could, of course, turn out that the simplest thing is also the best. All right, so some confusion, or a lot of confusion, I think, in the discussion, a lot of back and forth, has to do with not making the distinction between interpreting the effect within some theory or some framework and trying to arrive to some theory-independent line of argument. Because obviously one can demand that you give me a theory that somehow explains everything, so that's general relativity and quantum mechanics, and then you figure out how to put them together and it comes out consistent, and within that, what is the story that you see? And if you try to do that, well, I mean, there is an argument to be made that it's going to be an effect that is arising because of a superposition of spacetimes. But as I will say in a moment, there is many arguments and counter arguments and subtleties, which I think cannot be dismissed out hand. Some are smart points, and the only way that one could somehow get some clarity is indeed to see if one could arrive at a no-go theorem or a theory-independent line of argumentation, which might or not be possible for the type of experiments that will happen first in the future, which is, I think, also an important thing to clarify. Yes, so the effect is obviously predicted by simply putting together quantum mechanics plus Hamiltonian potential, which means that there is nothing to be concluded just by that. Just seeing the effect you cannot conclude anything. You need to add further input. And so the question is, what is that input that we want to add? In the attempt to get a theory-independent argument, even in a theory-fixed setting, as was said by Bose in the beginning, where they were basically doing QFT, they were saying that the main assumption is to input locality. So you want to say that, look, locality of interactions, we all believe in it because we've seen it in all the theories that are all space-time local, they're Lorentz invariant, and so on. But of course, there's an issue there that the type of locality that is being assumed is typically the quantum information notion of locality, which is subsystem locality, which is a very different thing than the relativistic locality of classical field theories like general relativity, or of quantum field theories like macrocausality. And the related, although somewhat separate issue, is that this, even so, even if you would have this clear, it is not clear what is the mediating degree of freedom you're talking about, that you would like to claim that that thing must be quantum. So, let me try to argue a bit more that there is the case for trying to arrive at more clarity, because it might seem at this point that we're all splitting hairs, which we might be. But I do think that there is still the possibility of getting more clarity of what exactly one might learn from this type of experiments. First of all, I like a lot this quote from Karlik, who's a quantum gravity guy, that one can take the line that the mixed classical and quantum models suffer from various inconsistencies, but in the end, one can only decide these things by experiment. And so you do want an experiment that will exclude mixed classical and quantum models. If it's not excluding it, then, I mean, you cannot say that you've seen something about quantum gravity empirically speaking. You can strongly believe it, but that's a different thing. So Jonathan obviously made this problem even worse by claiming that he has a theory now that is consistent about that mixes classical and quantum. And I think this old reference by Dyson that is very famous is relevant also, because if the graviton is not detectable, then, I mean, how can one assume that, essentially? If what we want to assume is that there exist gravitons to say that we have locality, and so that's the thing that needs to be quantized, well, you've probably assumed too much at that point. And I wanted to make a parenthesis here because I think this is interesting. I will not go into it. There is a recent claim that actually one might see the quantization of amplitude like in the photoelectric effect. So the discretization of amplitude in gravitational waves. Close parenthesis, that's another avenue that I think is interesting, but not very much related with the rest of the talk. There is these two very nice reviews that I wanted to reference from David Wallace and Nick Haggett. Actually, David Wallace also gave a key seminar on this that I forgot to reference. To cut the long story short, you know, you have all sorts of views on this thing. David is essentially saying that already if you require consistency, you basically already know that there must be quantum gravity. Otherwise, you cannot explain everything put together. Maybe on the other extreme of the spectrum, not extreme, on the other side, I don't want to put words in the mouth of people. The position taken by Haggett and al. Is that while it's not very clear if there is anything to be learned more than the COW experiment, we're talking about gravitational quantum physics, but not really quantum gravity here. There is arguments that by Bose and Anupa Mazumdar and others that one might really go deep in the quantum field theory framework. You know, you believe in QFT and so on, and you try to see within that theory how would you interpret these, and you can of course express the potential as being a superposition of virtual gravitons, and then, you know, the claim is that that's the mediator. There is a very subtle, nice discussion by Fragos et al. That even if one does put this input of relativistic locality that you find in quantum field theories, you still cannot conclude the quantization of mediators because it's going to be gauge dependent. And I will come to that, whether you have a mediator or not. Yeah, and just to put this out there too, there's even older claims by Magdalena and others that, well, actually we already know that there is quantum gravity from atom interferometry experiments back in 2014. So, and okay, I even have more references. Right, these are some very interesting recent works by Rick Persh and Eduardo, where they are trying to sort out what exactly is this regime that everybody's talking about in quantum information when they try to talk about field theory, which is the quantum controlled regime, is certainly not the general regime for quantum field theory. And what can we say about local mediators? So what can one say about degrees of freedom that are actually giving rise to the interaction that is making the entanglement? And there is all this discussion here about whether one should understand mediation taking place by space-like quantum fluctuations, or by making some argument about complementarity and causality that we need to input that and so on. These two papers by Hitaka et al. Are actually very clarifying, because they show very precisely that what is being talked about in these three previous papers is a completely different mechanism for creating entanglement than the mechanism that I will be talking about in a few slides, when I will be talking about the fact that entanglement is space-time local. It does not build instantaneously. Okay, I guess I've confused you, but it is confusing, which was pretty much the point. So let me try now to say what people are trying to find in my own understanding. I want to say this because I know that the crowd is both quantum information and quantum gravity. I think there is still a language gap, and this is how I've learned to think about these things, by talking to people like Czaslaw Bruckner. So one wants to mimic something like what's going on in the quintessential no-go theorem, which is Bell's theorem, where what you do is that you put clauses and you want them to be as few as possible. One has to do with experiment, and that's the one you want to go and tick. You want to go and do some experiment and violate some inequality and so on. And so you tick that. And it's a no-go theorem, meaning you cannot have all three. So either you're going to drop the other two, or you're going to keep one of the two. And what you want to do is that these two have to be things that you're attached to. That's a bit also metaphysical, that you want to have things that you don't want to let go of. And that's the value of having such a theorem, because it forces you into a dilemma. But note the subtlety that if you just have such a theorem in the sense of a mathematical theorem, I've defined a few things and I've proven something. It's not going to be interesting by itself. It's going to be interesting only if you know that there is some theory that you actually cherish as a community that goes through, and another one that you cherish that does not. So because you want to split, if you want, the space of interesting theories in two and say, oh, classical mechanics doesn't go through and quantum mechanics does go through. And that's the problem with the no-go theorems that have to do with mediating entanglement. It's not that they're wrong, they're theorems. It's that it's not clear if they're relevant, because the theory that we all like and want to see go through is essentially some sort of quantum field theory. Yeah, I want to just put an asterisk here that there are a few other attempts at no-go theorems that are not of this flavor, and I'm not discussing. But typically, therefore, the past few years has been in this direction, that what you want to do, again, is have, let's say, three clauses One is going to be ticked by experiment. You just wait 10, 20, 30 years, and Marcus here does the experiment, for instance. So that's done. And then you have two things that you know are important. So that's typically the locality of interactions and classicality. And of course, you don't want to drop both. You're going to have to drop one of the two, and the point being that you don't want to drop locality of interactions because you've seen it from other places in physics, and you're totally fine with dropping classicality of gravity. So that's the aim. But again, the problem is that even if you have such a theorem, and it's correct, you're gonna still need to show, even if this is a theory-independent line of argument, that there is a specific theory, at least one, that you do care about, that goes through the thing. Otherwise, it just becomes irrelevant. It's just gonna split the space of theories that nobody cares about. Okay, so in this direction, that's why we sat down, and that was one of the motivations of trying to understand what's going on with locality, because that's the input you want to put there. That's the thing you want to keep, so that you're forced into the dilemma of dropping classicality. So this paper somewhat clarified that by showing that entanglement generation in linearized quantum gravity, or in electromagnetism, or in scalar field theory, is taking place causally in a space-time local way, in the sense that the phases that create entanglement are being generated with retardation, so not instantaneously. Entanglement is not something that builds up instantaneously in the quantum state. Of course, this paper did not answer really what would be the mediating degree of freedom that one would be talking about, which is another sort of ingredient that is missing if you want to make these theorems apply to something like quantum field theory. The source of the subtlety there about the mediating degree of freedom and the difficulty in identifying it has to do with the following that I want to give a warning. So this is from the paper by Harris, a very thorough paper where they do a big analysis using the canonical formulation. But in the end, you see that there is this tiny section where what they're saying is that the transverse traceless part is gravitational waves. And so we're going to neglect that because, what do gravitational waves have to do with that story? And so, voila, what you're left with is just the Newtonian potential. But this line of argument is not accurate because you cannot do that. Why? Because it's wrong to think of the degrees of freedom of the field as radiation. That's only true in asymptotic infinity, or if you do not have matter around. If you do have matter around, then in fact, if you do that splitting, you would be talking about non-local degrees of freedom. And this is something that we discuss in this note here with Carlo and Richard and Andrea. It's very easy to see what I'm talking about in electromagnetism. I thought I'd show you these equations. So just take the potential of electromagnetism and split it in its Coulomb term and its and the vector potential. Then what you do is that you split the vector potential in a transverse part, so that's satisfying that the gradient of it is 0, and the longitudinal part C. From this splitting, you can define phi, which is a gauge invariant variable, and so is psi I, that's the transverse part. And it's very easy to see afterwards that the transverse part, so that's the thing you want to think of as the degrees of freedom, is satisfying a wave equation. And typically, as physicists, when we see a wave equation, we're like, okay, but that thing is going to have retarded and advanced solutions. So that's a wave that is locally propagating. And that's true insofar as the right-hand side is local in space-time. So you need to have a local source in order to say that something that satisfies a wave equation is a space-time local wave. But the source is not local because it's solving a Poisson equation. So that's the problem and the subtlety with just saying, yeah, it's gravitons or whatever. That's not going to work. Now, one cute way of going around this that is in this note is to go for some sort of global degree of freedom. There's a very easy way to show that there is a quantum coordinate transformation, of course, a quantum controlled one that identifies the proper distance as the degree of freedom that is being set in superposition. It's not local in the sense that it's an integral, but it's not non-local in the sense that you're breaking any sort of principle of locality of interactions. I think that's a cute direction. We haven't worked on it much more. Of course, it relates to a bunch of other work on quantum reference frames that I'm just giving one representative reference here. Yeah, I wanted to put it out there that maybe one should think about trying to come up with a no-go theorem that where the mediating degree of freedom is actually something being identified by a quantum reference frame transformation, like what we have here. All right. Now, this other paper here with Andrea and Carlo and Czeslaw and Richard goes a step further into identifying how one could talk about the mediating degree of freedom and making these no-go theorems fit into quantum field theory. And the way we did that is by doing a bunch of approximations, first of all, to the parametric approximations, which are typical in quantum information theory and in quantum optics. Because one should, not forget that there is no quantum field theory that's going to be subsystem local. This is never going to happen in full generality. Quantum fields are everywhere, even classical fields, and quantum fields have all sorts of other subtleties, like quantum fluctuations and highly entangled ground states and so on. But within the regime, and this is an interesting question because somehow the question here is how much can quantum field theory fit into the quantum information framework, and vice versa, whether you could generalize the quantum information framework to fit more of quantum field theory. So that is, one aspect of what is being investigated here. What one can see is that within the parametric approximation, where essentially you're quantum controlling the field, one can find a way to write the evolution of the field in what is mathematically defined to be a subsystem local evolution, meaning that you have these drawings here with the boxes, and the left and the right line is the left quantum particle, the right quantum particle, and the thing in the middle is the field. And the field is everywhere. That's fine. But what you want is to have your evolution be decomposed to admit at least one decomposition into smaller unitaries where there is no box that is touching both the left and the right particle. And indeed, you can do this. It's not completely trivial. It's not trivial, actually. If you also split the evolution into time intervals in which each source, in each time interval, the sources are in space-like separation. The reason is that you get an almost sublocal form of evolution, but there is this phase, this omega, which you can calculate using the Magnus expansion. And you see that it's integrals where the integrand is proportional to the field commutator. And so if you ensure that you have space-like separation, this is gonna be zero because of microcausality. And then you can prove that, okay, I can get a subsystem locality starting from relativistic locality. Now, this is still not, so in this sense, you can say that the thing in the middle, the mediating degree of freedom, is just a whole field, which is nice. But this is for a scalar field, what we did, and it still has to be done with a theory that has gauge constraints, which I was discouraged about, but recently I've talked with Eric Persch, that I've cited a couple of papers before, a student of Eduardo Martinez, and he thinks that there is a way to write this down with gauge invariant degrees of freedom and get the same thing for electromagnetism, linearized gravity. I don't put my hand on the fire, but that's a promising, I think, direction. Okay, now what else? Well, you can also try to do something completely different. Rather than going into all the subtleties of mediated entanglement and de novo theorems. I think that has to be done. And it's to think about Bose-Einstein condensates. So Richard gave a nice seminar where he explained this idea, that the idea is to just have a single system, not two systems that are interacting, and see its self-interaction, self-gravitational interaction, and look for a different indicator of non-classicality, which is the non-Gaussianity protection. Because if you start from a Gaussian state, like a squeeze state or a Gaussian, then evolution is not going to take you to non-Gaussian states if you only have two annihilation and creator operators in the Hamiltonian. So the game here is that at the same order of magnitude in the coupling constant, so in G, if you're in quantum gravity, because also the field, the gravitational field is quantized, you have 4 creation and annihilation operators. And so that's going to create a non-Gaussian. That's a very good idea. There are some follow-ups that I'm not citing here, I'm sorry. And there is an older idea about this by Lidner and Perez that is not about non-Gaussianity, but is somehow related. And there is a work that I was hoping we're going to have it out by today, but you know, we're good busy. It's going to be out very, very soon, where we show something that is quite striking, that you could simply go and measure the heat capacity of a Bose-Einstein condensate. I mean, I'm not saying this is, you know, easy to do, but if you could go and measure the heat capacity of a Bose-Einstein condensate to sufficient precision to see the self-gravitational contribution, you get a very clean distinction between semi-classical and linearized quantum gravity, because in one case, you get no contribution at all, while in the quantum gravity case, you do get a correction. I'm showing you here, these epsilons are the spacing of the energy levels, which is the thing that you calculate the heat capacity from. So I find this interesting because somehow this is what one might you know, consider a classical thermodynamical observable, the heat capacity. And indeed, it does know about whether it's a quantum field or a classical field that is doing the self-interaction. Of course, you know, we have not gone into all the subtleties that I discussed before. How do you know, have a theory-independent line of argument here? I don't know, but this gives you a clean distinction between semi-classical gravity and linearized quantum gravity. A different thing would be, so this is work with Gerard Higgins and Andrea. Very different thing would be to go directly for a test that would somehow not suffer from all the subtleties, because it would be genuinely relativistic. And what we thought about was to use the mass energy equivalence. So you take you take a superposition of rotating bodies that are rotating so fast that you get a contribution to their mass because of the fast rotation. So essentially you have a superposition of masses. And there is a game here. You see the suppression in the entangling phase by 1 over c to the 4, which you think, well, that's, kills you. But you do have a strong dependence on the velocity, and you could, in principle, rotate very fast such things. Now, Gerard and Andrea did a analysis of the constraints, of the in-principle constraints. One has to worry a lot about emitting radiation because of Bremsstrahlung when because there's a very involved protocol here of accelerating and decelerating. When you put everything down, you do find some regime, this small overlap here, that is in principle doable. Now, in practice, I imagine this is super, super difficult. I don't know how much more difficult than, the type of experiments that Marcus is going to do. Yeah, but this would be an effect that goes away in the limit of c goes to infinity. So this would be a generally relativistic effect, and it would also not have an analog in electromagnetism because the analog would be a superposition of charge, which you don't have. All right, and changing gears, and I'm almost done. All right, I'm just showing you some weird equations here to say that there is a line of work in loop quantum gravity that has been going on for many years. I'm citing my papers when I was a student that I was working on these problems because Carlo gave them to me. There's a bunch of other papers, it's not just this ones. It's a big, it's been going on since 10 years, I think, in loop quantum gravity. There's a lot of studies on that. And to cut a long story short, the picture that arises from loop quantum gravity, and there are some partial results that point into this direction within the theory, is that it might be, how to say, there may be many tiny black holes, now whether you call them black holes or white holes or quantum mini holes, whatever, is a different story. But there may be objects that are at Planck mass, which means that they have significant gravity. I mean, perhaps in Vienna they're going to measure the field of a Planck mass soon, the gravitational field. And there may be such objects which would be extremely minuscule because their radius would be at Schwarzschild radius, which would be Planck length. And so these objects would essentially not interact with anything other than with their gravitation because they just have a very small cross-section. So you just see empty space, even if they're passing through Earth. And so the only way to detect such objects, even though they're a very natural candidate for dark matter in this sense, because they're dark, they're not interacting with anything, they do interact gravitationally. And I mean, I'm not saying it is like that, but if I would bet, it sounds that pretty plausible to me. But if that's the case, then how do you detect them? Which is somehow, the problem. And first of all, one has to appreciate that there aren't so many of them. There's about one passing every year in every square meter on Earth. So one would need to think of a one-shot experiment. You don't have the luxury of doing, taking many, many events and reconstructing statistics. Last summer, we put out this idea with Alejandro and Carlo that we're very excited about on how to somehow put together all the stuff I was talking about before, the main ideas, and calculate the phase. There's no entanglement involved here. You just put, you use a delocalized mass as a sensor, and there is the dark matter passing through. It's passing through at 100th of the speed of light on average. You can do a calculation and get the phase, which is this formula here. And that's sort of the Gedanken experiment. And then you can think of a specific protocol that we thought using Josephson junctions, which is somehow striking. It might sound stupid, but actually the numbers seem to work. Because the mass here is going to be the mass of the electrons that are delocalized across the junction. And yeah, it seems that it's not completely crazy. I mean, I'm not saying it's easy, of course, but it's not completely crazy to maybe go out and build the detectors that would be able to see these tiny black holes or white holes passing. Yeah, I leave you with this slide. Thank you.
Brilliant. Okay, thanks very much, Marius. Thanks for a really nice talk. So I'll say to people, please raise your hands in the chat, and then we'll go for any questions people have. So we got a question from Carlo.
No, I was just clapping.
Oh, sorry. Great. Cool. Yeah, does anyone have any questions? Toby.
Hi. First of all, thanks a lot for your very nice overview talk. I don't know much about the field, so maybe my question is dumb, but you have talked a lot about entanglement between gravitating objects as some way of detecting that the field is non-classical. But there are, of course, also other quantum effects which don't need two parties. Like, for instance, optical non-classicality, something which is directly related to a single body or not two. Can one also, or have people thought about these kind of things as witnesses?
I'm not sure what you're referring to. Yeah, can you explain a bit more?
Yes. Okay, sorry. There is this notion of non-classicality of a state. For instance, when the Glauber distribution does not behave like a probability distribution, or when the Wigner distribution is negative, these kind of things. And they all show that this cannot be described by a classical theory. And the reason why I'm asking this question is because for entanglement, you need at least two things, whereas quantum object can be non-classicality by itself.
Yes, so okay. So if you see the talk by Plenio and the paper by Plenio, I don't remember where it is. He's analyzing mediated entanglement here on the origin of force sensitivity. This one, he's doing the analysis using Wigner functions. And on the more general point that you don't need to do it with two, this paper here with by Richard, this is essentially the idea. The Wigner function is becoming negative when you're producing a non-Gaussianity. Now, yeah, I'm sure there's many more to say about what you're asking, which, yeah.
Okay,
I'm not sure how
thanks.
Okay, good. So I'm just keeping an eye on the participants list for anyone with a raised hand for a question. Okay, great. Richard?
Hi, nice talk. Basically, I just wanted to ask a little question about experiments in relation to quantum computers, or at least the things that are being built that are supposed to be computers. Because I know in some of your papers on like masses, superpositions of masses in different positions in relation to some gravitational object, like it's usually in terms of like individual states and individual masses, but presumably in the future, we might be in a position where you can have quite a lot of masses, relatively small ones, controlled in superposition on mass. At the moment, incredibly noisy, but maybe not always so. Is that something you've thought in the direction of, and how you might take advantage of like the scale there to amplify probably features you're looking for?
You would get the 1 over square root of n. I have not personally looked into that, and I'm slightly embarrassed that I don't remember the papers who did that, but there are a few papers.
Okay. Thank you. I'll have a look for them.
Yeah.
Okay, Francesca. Just so you know, you're muted.
I behave like an academic grandmother. Yeah, so I was saying that I would like to continue on this, just a comment and a question for Marius, because I received recently a question related to this, presenting a talk on remnants. And the question was about whether we expect to have eigenvalues of the mass or not. So the question, so in relation to what Richard was asking, I think that it depends on in which way we are doing the measurements, whether we are measuring in a basis that diagonalize the masses or not, because in this case, okay, you can see a superposition, but it would be a superposition of eigenstates with very precise values. I don't know if you have thought anything in this direction.
No, let me just guess. First of all, so what you're saying is, if one interprets this tiny black and white holes as a superposition of black and white, like you were doing in this paper with Carlo, if you would see some discrete spectrum of the mass, is that what you have in mind?
Yeah, I mean, yeah, something in this direction. Yeah.
Sounds interesting though, but okay. Were you seeing something like that in that paper? I don't remember that.
No, the point is that you have different observables. I mean, usually we think in terms, so when we discuss these objects, we think in terms of the usual canonical variables of quantum gravity, that is the area and the curvature. So what is in the superposition there is the curvature that could, the extrinsic curvature that could be positive and negative at the same time. So, but if you want to measure in particular masses and see superposition of masses, then I don't know if maybe we should think in a different way, because it's like measuring in a different basis. And again, whether we can see superposition of masses or if we see eigenvalues for these objects. So I don't know, because this is a question that I got like a couple of days ago in a talk that was related to this, and I was puzzled myself, and I wanted to ask you about this the first time I would have seen you. So
I've not thought about it, but I mean, one has to see if one can make a reasonable argument for it. But that sounds nice. So what you're saying is that, okay, you're gonna detect them, but then maybe you're gonna detect you know, a quantized force essentially on the sensors, and this is going to tell you about some discrete geometry. I mean, it would be really nice if such an argument could be made. I've not thought about it. Yeah, but I see what you're saying. That sounds nice. Yeah, could be, because it's a tiny thing, so it's going to be sourcing, you know, a near, how to say, the geometry is going to, you cannot have it infinitely curved, right? It has some bound, and maybe you're hitting that bound. That's what you are thinking. Yeah. I don't know. That's interesting.
Okay, Philip.
Thank you very much for the nice talk. On the slide that you're showing, you mentioned non-Gaussianity as a signature of this quantum gravity. I'm wondering if, you know, there are other types of condensates, of course, right? There's these phonon condensates where you have population inversion in these complex systems. You have, you know, even in a laser, you have population inversion, a type of exciton condensate, I suppose. And then you even have these kind of Froelich condensates in other, you know, biological systems. Do you think that there might be possibility in a less extreme regime of these tests with other types of condensates that demonstrate non-Gaussianity? Or is there something particular about Bose-Einstein condensates that is required for these tests?
Well, what's particular about BCs is that they're the simplest one, and we're not very good at this stuff. So that's
Sorry,
why.
I didn't hear that.
So basically, it's the simplest system to look at, and we're not very knowledgeable about these things. So that's all we could do. So I think it is very, so thank you for the question, actually. I don't know about phonon condensates, but one thing that we've been discussing, which is obvious, is that it's a bit silly to think about Bose-Einstein condensates in a sense, because it's the most dilute thing that you can think about, basically, right? It's like 1,000 times more dilute than air or whatever. And you're talking about gravity, you're talking about self-gravity, so you actually want the densest thing possible. So the reason we did Bose-Einstein condensates is because the theory is more manageable. You know, you have all the Bogoliubov approximations and so on that are somehow standard, and you know, because we could somehow navigate ourselves through the literature and say something that is not going to be plainly wrong. I know that Richard Hall is discussing with experimentalists on superfluids and theorists on superfluids, and that's the obvious thing to look at something that's more dense, because naively you're going to get a huge amplification because of the mass density, because this is gravity. The problem, of course, is going to be whether, you know, it's not just getting a bigger gravitational signal, you have to also be able to say that you're going to tell it apart from the electromagnetic interactions. And the physics are much more complicated in superfluids. You don't also have the possibility of using Feshbach resonances to tune down the electromagnetic interactions. So it is something that interests me. I don't have, you know, unfortunately, I don't know so much about it. So I'm going to rely on collaborators and so on. But it's an obvious thing to look at. I don't know if there's any hope for getting something, but looking at more dense macroscopic quantum systems is, yeah, an obvious thing to investigate.
Yeah, no, just a thought. There was a nice paper in PRL in 2019 from Marlon Scully's group about showing these phonon condensates as a, you know, a product of the nonlinearity in the coupling to their local bath. And so it's it's much easier to handle than a Bose-Einstein condensate experimentally. So I don't know if but it's a different parameter regime. So whether the coupling to gravity, I'm curious if people have thought of other types of condensates that exhibit this non-Gaussianity and whether that could be used.
One has to see what's the, you know, the effective mass that is going to be going into the coupling with gravity to understand if that's a good direction or not.
Thank you.
Okay, so I'm keeping an eye out for more questions, but I can't see one right now. So I'll take the opportunity to ask one myself. Okay, so at some point you were writing some analogy to Bell's theorem. And you had a slide with a couple of lines, and I might have not completely followed, but I think you were saying that, like, you know, it's an important theorem because it says something. It says something because we have a theory that we care about, that we hold in high regard, that gives us A.
At least one that goes
Yes.
through.
At least one. Yeah. So being a bit naive about it, I would have assumed that with these no-go theorems for that come from like tabletop gravity experiments and so on, that like the theory that we hold in high regard that makes predictions in this line would be like something either quantum loop gravity or something made from it in some limit. So is there some reason why it's not as obvious as it is in the Bell's theorem for quantum theory that these no-go theorems that you're talking about say something about quantum loop gravity, for instance?
So, I mean, the story would be, I guess, don't think anybody has thought directly on loop quantum gravity. It's actually easier if you think about it directly on loop quantum gravity, but somehow the way one would think about it is that loop quantum gravity, as, you know, also string theory, loop quantum gravity somehow has demonstrated that there is a low energy limit that gives you back something like quantum energy calculus, and by extension you would get something like linearized quantum gravity. And this is, if you want, one of the things that these two worlds agree on, at least on the expectation that they want this, as the lower energy limit is somehow incontroversial in the quantum gravity world. So then you just go and talk about that, about linearized quantum gravity, and you can take higher corrections to it, doesn't matter. The point is that this is now something that looks very much like a quantum field theory with gauge constraints like electromagnetism. And in that framework, is not clear what it is that you would be calling locality, right? Because when they prove these theorems, it's more quantum information, quantum foundations people, they assume local operations, but by local operations, they mean subsystem local. They mean I have some decomposition of the Hilbert space and, you know, have identity on one paradigm acting on the other one. But this doesn't translate in any easy way on what's going on if you have some field in spacetime. So that's one issue. That's why we were trying to see how you can get subsystem locality, which is the quantum information notion of locality. If you want, which system am I acting on? But it doesn't really matter. You know, I mean, it could be subsystem local to the polarization degree of freedom of a photon, and it's, you know, it's the same photon. It's more about splitting a system into subsystems. And a related thing is what I was saying, that you need to say what is the state space of the thing that you want to call a mediator. And if it's just, you know, for instance, if you just take the Newtonian potential, and that's why it wouldn't work without an additional assumption of locality, it doesn't have a state space. So there's no system to talk about. Now, it's very hard also to take a quantum field and split it into regions in any way that makes sense. It's even hard for a classical field, and it's even harder for a quantum field. So somehow you have to take a whole field to be the degree of freedom. But if it's a whole field, how are you going to talk about locality of interactions and so on? These are the, you know, hairy things that we're trying to sort out. And somehow you try to start from a field theory where you have done some assumptions on the source and show that you can encode this on the quantum circuit so that you can use something like general probabilistic theories and direct theorem. That's somehow the game, and there's many people trying various aspects of it.
Okay.
Was that clarifying?
Yeah. Yeah, it is. Yeah, that's really interesting. Okay, I'm gonna mull on that. Thanks. Cheers. Martin?
Yeah, thanks. Maybe here I would like to ask, but I'm coming to this from the quantum information perspective. But I read some of these papers, especially the one by Fragos, where they try to explain that the thing mediating the interaction are not the physical gravitons, but these auxiliary particles that cannot reach infinity and stuff like that. And then I wanted to ask how, in principle, can one do this subsystem splitting? Because when the system in the middle is not something that you can send to infinity, or when it's not a physical system, because I think this is somewhat of an assumption in the LOCC argument that the middle system is a physical system and not some hypothetical thing in equations.
I'm not sure I caught the question exactly. Can you say again, please?
Yes, so I was just a disclosure is that I'm coming from quantum information, and I was trying to read up some literature on this, and there is this one paper by
perfect.
I'm sorry?
Nobody's perfect, that's okay.
Yes, and there's this one paper by Fragos where they explain that the gravitons that actually mediate the interaction are these auxiliary gravitons that are not physical objects in themselves. And then even if this subsystem splitting is done, how does one deal with the non-physicalness of the system in the middle?
Yeah, that paper is giving me trouble. It's a very nice one. It's this one here.
Yes, exactly. Because then, for example, one can assign something like virtual negative probabilities to this. And for example, in quantum info, we know that if you can locally generate negative probabilities, even if you never measure them, you get loopholes in Bell experiments and everything. So this is bit scary to me personally.
Yes, I mean, I agree. And as I was saying, you know, I'm not aware that there is a story that holds together if you want to go for a no-go theory. Now, with respect to this direction in particular, you know, there's somehow subtlety that they point out has to do with choosing different gauges and essentially saying that, look, I'm gonna assume your relativistic locality, but you know, in the end, you would like to, as I was saying before, to take the field and call it the mediator. But if you're doing a gauge theory, it's a gauge field, right? It's not like a scalar field that is your actual physical degree of freedom. And so you start changing gauges, you start changing also the description of it. And you can go from a description that is subsystem local to a description that is non-local, where they mean subsystem non-local. And that's why I was saying that the one step in this direction could be made if one takes the story that we did here and does it in a gauge theory, which Rike, that is a student of Eduardo Martinez that has written a couple of these papers, is visiting Vienna now. And we have some ideas on how this might be done, and this might answer that concern, but we'll see. It's a valid point that they're making.
Yes, I understand. I'll definitely read this paper of yours. I just mean that can you then actually assign a Hilbert space to the system in the middle and things like that?
Yes, and you want it to be gauge invariant.
Well, yeah, okay. As long as there's Hilbert space, that's nice. Thanks.
Yeah.
Okay, and just keeping an eye out for more questions. I don't see any at the moment. We'll just give people a couple of seconds to. Well, okay, actually, while I'm waiting, I was wondering, you made a comment in your answer to me. You said that even in classical fields, it's hard to split things up into regions. You made a comment along these lines. I was wondering, is it easy to say why that is?
It's for what I was saying here. This is classical field theory.
Right.
The field is a field, essentially. It's all of it. I don't know if, let me put it this way. If okay, what do we mean by degrees of freedom, right? You want something that is giving you a complete description at every point in space-time of the field, and you want it to be gauge invariant, right? Because you don't want it to be a fiducial thing. You want it to be the real thing, and you want them to be independent. Now, if you could do that, if you could write it down, then Maxwell would have thought of electromagnetism as a theory of two scalar fields. He wouldn't have written down the gauge theory. All right. I don't know of a way to do that. Or every way I've seen, it's something we've been thinking about also with Carlo and Andrea and Richard and others. Every way you find to write down these degrees of freedom is non-local in space-time. You know how to count them. You know how to count the number 2, and you know how to say there's 2 gauge invariant ones, but you don't have a way of writing them down. Otherwise, you would just have, you know, both linearized gravity and electromagnetism as a theory of 2 scalars. So it's not some, how to say, it's not strange that you have this problem if you want to encode this in a circuit language. It does touch on very foundational, you know, questions like why gauge theories and so on, which I find interesting.
Okay, thanks. Cheers. Okay. So I think I can't see any more questions coming up, so I think that's probably a good place to wrap up. So, yeah, since there's no other questions, yeah, I'd like to say thanks very much, Marius, for the really nice presentation. It was really nice actually to have an overview of so many different bits of work. I think that was very relevant to this seminar series. So I think I think a lot of people, including myself, are going to find this very useful, and I'll probably watch this quite a few times. So yeah, thanks very much. And yeah, thanks for the presentation and the discussion, and we'll end the formal presentation there. Everyone can thank Marius. Yeah, and see you all soon.
Thank you,
Okay,
Matt.
so we'll
Thank you
thanks.
for everything you're doing.
Cheers. Okay, so I'll just stop the recording and the live stream now.
Yeah.